So thank you very much for the wonderful playing. And I would like to ask Michele to deliver his award lectures.
What should I say? A big thank to everybody. It has been really great. Thanks to Goffredo for his wonderful summary. I couldn't have done better, I must say. And of course, when I received a letter from Professor Delago announcing me, came to a big surprise. I didn't know, I never expected, and so on. Also, in the letter was specified the people that had nominated me, and whom I didn't know, or if I knew I met somewhere. So they were unknown people to me. That was a special pleasure. Also, there is a special feeling for being in Vienna. Okay. Vienna is one of the great places for science, in the past and also in the present. If you've seen, I don't, but I mean, there are very many great scientists in Vienna, so they continue this big tradition. And so what I to see, it's very, don't worry if you cannot read it. I will explain what it is. There is a site on the web, I think it's a gentleman from Hanover, that in his retirement ages decided to produce this site where you do the academic genealogy of people. So I went to this site and I put my name, and it's a big tree. That's only the left part. The right part will come later. So that's me. My professor in Bologna was Ferretti. Ferretti studied with Majorana, not the big Majorana, but he was still an important scientist at the time. And then he studied with this Pietro, I can't know, but then here we go. We arrive at Vienna. Well, Attinghausen. But it's more interesting to look at the right-hand part of the tree. That's again me. Ferretti studied with Fermi. And then via Ehrenfest, we got to Ludwig Boltzmann, none else. So more Vienna than so, and this is difficult. Yeah, I can't. So Vienna is a part, it's in my destiny. And it was mentioned by Christoph that I spent a long time in Trieste and at ICTP. ICTP is very close to the Miramare Castle, so that's the first tragedy with Vienna and Miramare Castle. Charlotte and the husband went to this fated expedition to Mexico from here. Rather than enjoying the sea, he decided to become Mexico emperor. And this is Boltzmann as a young man. He looks very different from the grumpy old man that usually we see, actually handsome, with brilliant eyes, who committed suicide very close to here. So on a less dark side, there is a big feeling in Trieste of the importance of the relation with Austria. In fact, I think many people regretted that Trieste went from Austria to Italy after the First World War. And here, this is Marie-Therese of Austria. It's a big thing in one of the main squares of Trieste. Okay, so usually when you receive a prize, you talk about what you have done in the past. And in spite of my old age, I want to talk about what I'm going to do in the future. And so I'll set up, so this is the program, set up the scenario. So we'll talk also a bit more about the committer. So introduction, the need. Also, the Goffredo talk has been very useful. So I don't have to say many things, okay, the relevance that machine learning and this enhancing sampling method are having in pushing forward the boundaries of molecular dynamics. And in particular, machine learning, which I think is cure for the curse of dimensionality, really. At least in the application that I do, that's at the heart of what we do. So we can do things, so for instance, I will talk later about Fokker-Planck. If you look at the equation, if you go beyond one dimension, you're totally lost. And now you can do multidimensional things. So it's a great thing. Okay, and in fact, so that I think I feel like Alice in Wonderland. I'm going through these tools, and also the community, I think, through Looking Glass, where you see all sorts of new things, monsters, the Mad Hatman, the Cheshire Cat, and so on and so forth. New kind of physics, a complicated chemistry, which it would have been very hard to imagine before doing the simulation. And we can now look, for some reason, have got interested in catalysis, and catalysis appears to be much more complicated than we believed, with all sorts of phenomena taking place at the surface, phase transition, collective effects, and so on. It is a very rich and interesting field, which we physicists should leave it to the chemist. Okay. And also, there is an issue of complicated system, which even if you do the simulation, it's very hard to understand what they tell you. So I take this example from the literature, since I'll talk about these proteins. So these are proteins which don't have a well-defined structures, and it's a majority of the protein, and they're very important in many diseases. And the people that think they are undruggable, but in fact, they're starting to think. And if you look at, say, AlphaFold, that's totally helpless in predicting what happens, let alone understanding, which is, say, for folding, we are the situation there is predict the fold, but no understanding of what happens, how it happens. Okay. Another thing, real-life chemical processes are very complicated. Often the results are described in this way. They take a very long time, and you first produce, in this case, hydrogen, then ammonia, then this and this and that. So complicated, in which you have many reactions taking place at the same time, which change the environment, change the system, and evolve in time. Can we handle this? Okay, so this is a justification, and we have new tools, as I was telling you earlier on. We can simulate ever more complex phenomena, but often we got into the point where understanding what happens, it becomes the challenge, not the simulation. And so I suggested that I think many other people, but I mean, must have said the same thing, but that we should change our point of view, rather than looking at single events, or sequence of events, one needs to force to the probability distribution that evolves, like in the case of the reaction. So the probability distribution at the beginning evolves. And you don't want to follow every single little details because you get lost. You cannot do it. Okay. So that's what the justification. So this I've already said, but just to remind you that this is, of course, it's not new. In physics, since a long time, we have complicated phenomena like liquids and so on. They are described by hydrodynamics equations, which are relatively simple and very useful, and you don't follow each single atom does as it moves in this complicated system. Can we move in that direction? Okay. And so that's why I say. And so we are trying to move in this direction. So ideally, one would move, say, from Newton's to Fokker-Planck. Fokker-Planck is a really, even with machine learning, it's a very, very difficult and complicated thing to look at. I get scared every time I look at the question. But fortunately, there is a formulation due to Kolmogorov. It's called, I don't know whether historically it's really Kolmogorov, but it's called the Kolmogorov backward equation. And that's what I'm going to talk about. So rather than looking in this equation, rather than looking at the evolution of the distribution at time t, we look at deviation from the equilibrium distribution. That simplifies enormously the equation. In fact, you can write the evolution of this deviation in a form which is very familiar. So earlier on, in fact, Georg Kresse has shown a similar equation where instead of L, he had the Hamiltonian. So it is a structure with which we are familiar. We have been educated at looking equation of this time since our childhood. And of course, here the dynamical operator that generates this dynamic is not Hermitian, but is pseudo-Hermitian. They say don't know really well what happens from what concerns us. The eigenvalues are positive, and you have to worry about the right and left eigenfunctions. But that's not a major problem. And there are even more interesting properties. So if you diagonalize, and then you have eigenfunction, eigenvector, you can represent the evolution at time t as a linear combination with the coefficient which depends in time exponentially, because you want the thing to go to the Boltzmann distribution. So it's a relaxation dynamics. And these lambdas start from 0. So if you start with the Boltzmann distribution, nothing happens. And then the eigenvalues are positive and greater than 0. So to get familiar with these eigenvalues, we consider this little example. As I said, the 0 is a trivial eigenvalue. More interesting is the first eigenvalue, which is this change here, this jump. And in the step is really in sync with the highest transition state. The second is in, so you have a step here, and then the other is a step there. So there is a correspondence between these nodal surfaces and the structure of the Hamiltonians. And another thing which is interesting from the practical point of view, although this seems a complicated. The matrix element of this operator don't involve second-order derivative. Can be written like that. There is Dirichlet. I just discovered Dirichlet is not French. It's Prussian. I have a French student, and he quoted this thing, you're the chauvinistic, always French, what the French, it's not French. It's Prussian, in spite of the name. Okay, anyhow, so we have, it's like having the Hamiltonian. So this is a simple case. You can do everything on the computer, sort of analytically, exactly. But when you have a more complicated situation, you have to do what is done in quantum mechanics. So use variational principle to find the smallest eigenvalue of this operator. And so you get the loss function. I'll try the details of, and it's not as simple, and I must acknowledge here these three people. These are team is the Dirichlet guy, and Vladimir is a Serbian mathematician, and Massimiliano is also a mathematician. Is my colleague at IT, and in particular, Vlad found a very tricky way of expressing the variational principle in a form which is very stable. The ingredient that you have to calculate is this matrix element and the overlap matrix. So you can do. So in fact, you need only static quantities to get this dynamic information. And in fact, you can calculate these eigenvalues even using bias equations. So you take a bias simulation in which you change the dynamics as you go along. You can get through reweighting this eigenfunction and eigenvalues. Okay. Let me show a little example. Example, again, a toy model of this little protein, which has essentially 4 metastable states, which are spanned by these 2 eigenvalues. I can crank this machine and look at the eigenvalues. As expected, they tend to have a nodal surface where the transition state is. You go from this regime to other regime. So another second eigenfunction is this direction. The other is kind of this direction. I go look at the eigenvalues. I have 3 small eigenvalues. I go to the 4th. Wow. 3 orders of magnitude larger. So that means the mode associated with 4 decay so fast that they're really irrelevant. So all you need to do to take care of, if you want to study the long-time dynamics of this system, of this 3 state. So you go from a description in 3n variable to a description in 3 with 3 functions. Okay. And I show how I start a simulation with the distribution here, and I see it evolve, and the probability spills over to this state, then spills to that. Eventually, it goes to the lowest eigenstate state, which is this one. And I can transform this in occupation number. So the occupation number was 1 here, and then it decays almost to 0. This goes first to here, and then decays to 0, and in the end, only 2 eigenvalues survive. And this I want to point out your relation between this and the other. So they are the same thing. I mean, of course, this is infinitely more complicated, but that's where we want to go. The other thing I was again, it's a way of describing complex systems in a simplified way. So we have a collaboration with this company in Switzerland. They are trying to produce drugs for disorder protein, which are very, very terrible, and of course, AlphaFold describe them poorly, if at all. Okay, so this can be done relatively simple with our model. So there is a simulation which we can take, calculate the eigenfunction and eigenvalues. Then we cluster the data around 4 different states. And that's how it looks like. This is the ground state, and there's one excited state, and the other excited state. If I, okay, and that can be useful for drugging. But I just want to contrast this simple, back, the very beginning. Okay, it should be, you see, I forgot to move this thing forward. So this is the same protein that I was describing, which has 4 states, very clearly identified, and that's the analysis that, heroic analysis that this group has done of the dynamics of this protein with millions of kinetic Monte Carlo states. So there is a economical description of the system that allows you to understand and move forward. Okay. The last bit will be about committer, which was being alluded to, and I don't have to say much because it's been said, but briefly, if I have this two-word system, I can describe the situation by looking only at this state, and the other state. I can look at reactive trajectory, but to me, the most satisfactory way of describing this rare event situation is through this probability that gives you, if you start in X, what is the probability of going in B or going back to A, and this is this step-like thing which we use, and then why did we do that? It seems that it's very difficult to do, but in the hypothesis of overdamp dynamics, which is the limit in which we kind of work, has written a partial differential equation for this committer, but the solution can be found as a minimum of this functional subject to this boundary conditions, 0 here, 1 there, and at the minimum you get the rate. I will not go into the details, but just praise these two fantastic postdoc collaborators which have written two great equations. We not only solve for the computer, but we can sample all the states, and that's the wonders. Okay. You can start anything and gives you a very, very nuanced and I think a right way of defining the transition state, not as a single point, but as a distribution. Okay, so classic example of rare event is crystallization. I think where there are some fantastic works by Christopher Delago. We retried everything and we learned a few extra things. Okay, and you can retrace the whole result, but with a different twist, which I don't have time to go into. Okay. We can study transition in which different pathways are possible. This is a small protein, and it can, which can be looked at as hairpins, where there are two series of bonds that keep the thing together. At a certain point, one tyrosine disentangles, and then two roadways can be taken. In the first one, which we call down, you break the upper bone. In the other, you break the lower bone. And then eventually you go to the unfolded stage. Okay, so quickly, because so I just want to show how useful this method can be in real problem. Okay, one real problem is this, plastic is a major scourge, disposing of plastic of modern age, and so people in desperation, they are thinking of using enzymes which are able to chew plastic, in particular PET, and of course the efficiency of this approach is not optimal, and so the idea is can we do something to make this enzyme more efficient? And so we have used our methodologies and studied two enzymes, PETs, and the very recent one, and to cut, we can again follow different pathways, which is quite a unique possibility, property of our approach, of our committer. I mean, that's Kolmogorov. And you see, they're very different. The reason why I show you is the nature of the transition state changes. So in the pietase, petase is a single transition state. Instead, in the second, there is the chemical the transition state has been stabilized, and this makes the protein more stable. On the basis of this, we can start playing with the residues and try to optimize it. And that's we can proposing that a double modified mutated protein can be very efficient, and this work is the main actor is Alessandro Berselli, and we are doing in collaboration with the University of Modena, Reggio Emilia, and the University of Porto. And with this, I thank you for your attention. Thank you for the prize. Thanks for the warm welcome. Thank you.
Thank you very much, Michele, for a nice overview of your current and future work. Very, very nice to see.